Okay, cool. I have another notebook if you need one. I was gonna say, I have more notebooks. So I could grab one of them and whenever you need. I've got, especially composition fine type. I've got tons. Okay, so what we're working with next is going to be something called the dot product. And it's very much like multiplying. The only thing that makes it different than if we were just like adding our two vectors together or subtracting our two vectors together is it doesn't give us a new vector. It gives us kind of a idea about their relationship and how close their angles are together. So to find our dot product, what we do is we multiply the x pieces together, we multiply the y pieces together. It's going to give us a number. This is not giving us a vector. We multiply the x's, we multiply the y's, and we add them together. It gives us a number. There's a special word because mathematics likes to make things complicated, meaning that they are perpendicular, which the word for that is orthogonal. It just means perpendicular if their dot product is 0. So if we do the dot product and we get a 0, that means these two guys form a 90-degree angle. And they're parallel if you can multiply them and get there. So if I could take A and multiply it by 2 and get to B, or if I could take B and multiply it by 7 and get to A, that means they are parallel. So if they are a scalar multiple of each other, they're parallel vectors. If their dot product is 0, they are perpendicular. If it is anything other than those two, they're neither. So what we're going to look at today is we're going to look at finding dot products and figuring out if they are orthogonal, parallel, or neither. So that is what we're going to do for this today. So I'm going to give you a second to write these down because I know there's a lot of words on this page.
The most important one is orthogonal because that is a word that we use. Okay, orthogonal. No idea why it's orthogonal, but it is what it is.
I have no idea of the etymology of that word. It makes me think of orthodontist. Slowing down. Oop. All right. I'm going to give us a couple of vectors. We're going to find our dot product, and we're going to see if we can figure out if they are orthogonal, parallel, or neither. So here's two vectors. We've got vector u as 3, -2, and vector v as -5, 1. So first thing we're going to do is to find the dot product. What that means we're going to do is we are going to take vector u dot vector v. So that means I'm going to take my x pieces, so my 3 and my -5, and we multiply those two pieces together. And then we're going to add, doing the same thing with the y pieces. Take my y's, the -2 times the 1. I just blinked. What did it do? Nothing. We love that. Well, those are all operations we know. 3 times -5 gives us -15. -2 times 1 gives us -2. 15 or -15 plus -2 gives us -17. So the dot product of u and v, so u dot v is negative 17. We're going to use this for several things over the next couple of days. So the fact that we don't know what that's telling us is totally okay. So this is our dot product. That is the first thing we're asked to find. We found it. Find the dot product. That's this guy. Ta-da! To see the relationship between, we want to know if it's orthogonal. It is only orthogonal if the dot product is 0. Since negative 17 is not 0, we know it is not orthogonal. I'm just going to put orth because I can never spell orthogonal. Even if it's written on the page in front of me. I will still misspell it. The really only thing we have to think about is if it is parallel. So I want to know, is there anything that I can multiply one of these by to make it wind up as the other one? I was going to say, we don't really have much that would get 3 to be negative 5. That would also take 2 to be 1. I mean, if I took negative 2 times negative 1/2, I would get to positive 1. But if I took 3 times negative 1/2, would that get me to negative 5? So I would need to have the same number that got both there. Yes, dear?
Does the sign also have to be the same?
Yes, it would need to match it exactly. So since there is no number that we can multiply this by, these are not parallel. Because there is no number that I could multiply u by to get to v. There's nothing. That looks like a check mark. I cannot get some number to times by u to get to v, or the other way around. Either way. So that means that these are neither parallel nor orthogonal. So orthogonal means our dot product would be 0. So if we get a 0, like it straight up answers all the questions for us. If we don't get a 0 there, we see if there's a number that'll multiply between them. And if we can't find one, it's neither. We're going to try a couple more of these. So we can see what all these things look like. Okay. Questions on this first one. I know it still feels like we're doing magic. I'm giving us another u and v. So if we have u of negative 2, negative 3, and v of 9, negative 6. Same question though. We want to find our dot product, see if they're orthogonal, parallel, or neither. So we're going to take our u dot v. I think I hear some of you working faster than me, and that's okay. So we take our x pieces and times them together. So we're going to have our negative 2 times our 9. And we're trying to add our y pieces to it. Our negative 3 times negative 6. Well, those are all operations we know. Negative 2 times 9. Negative 18. Negative 3 times negative 6. 18. Negative 18 plus 18. 0. Go for it. 2 overlapping questions, but I can only hear one at a time. Go for it, somebody. Okay.
Are they going to be operations we don't know?
No.
Oh, you were saying
I was going to say it's always going to be, I'm just going, we know how to multiply. Don't freak out. They're vectors, but it's just multiplication. Everyone looks at this and goes, I'm expecting this to get really crazy here in a second. It's not. Like, dot product is multiply the pieces and then add those things together. It doesn't, like, we're going to use it in a couple of things, but dot products don't get worse. Like, this is what they are. Okay, so our dot product is 0, which means what do we know about these two vectors? They are perpendicular. Our word for that is our orthogonal. Every time if I try and write it, it's gonna be like orthodontist. But that's about as far as I can go without having to look at it. Oh no, there we go. Orthogonal. It's weird. Ortho. That ortho is like super funny for me. Like totally get it. Okay, so since our dot product was 0, they're orthogonal, meaning they're perpendicular. Okay, we'll do one more. One more. So we're going to find our dot product here of our u and v. We've got u that's 2, -10. V is 1, -5. So our dot product here for u dot v, our x's we multiply together, 2 times 1. And our y's we multiply together, -10 times -5. 2 times 1 is 2. -10 times -5 gives us 50. So our dot product is worth 52. Say it again, I couldn't hear you.
Word is 0. What is the word? I'm not saying the word.
I was going to say, a big clue on that is like orthogonal starts with an O, which is mostly a 0. So if your dot product is 0, it's the O. So we know for sure they're not orthogonal. Why? Yeah, you can multiply u by 1/2, or I could take v times 2 to get to u. Because 1 times 2 gives me 2, -5 times 2 gives me -10. So these are parallel. Okay, so that's what we're starting with our dot products. We will work more with our dot products tomorrow. Okay. So 8-4 is back in the book. Of course we do, just saying. I was going to say, it's not a worksheet time, it's back in the book. Yeah, homework. Yes, of course we have homework, just saying, it's here. Okay, so it's, I guess it's not until next week anyway, so like, we're good.